Here's my contact information. I've been doing JRuby for years at various companies, having a lot of fun with it, and learning a lot about how the JVM works internally, trying to communicate that to other people, trying to find better ways to make Ruby run on the JVM and help other JVM languages. And one of the earliest adopters of Invokedynamic. The minute there were even early draft builds of it, I was trying to put it into JRuby. And we actually had it in releases of JRuby in 2008, well before it was even committed to OpenJDK's repositories. So I've seen it from the beginning, and I'm still following it along as it goes. All right. So here, this is what I truly believe. I believe that Invokedynamic, more than any feature that's been added in the past 10, 15 years, is going to completely change the future of the Java platform. It opens up so much possibility. Hopefully what I'll be able to communicate to you today is why that's the case. Okay, a little bit of history. So even back in the original JVM specification, the authors of that spec, Gosling and others, did mention that they could foresee a future where non-Java languages would run on top of this VM. They were building a nice platform, a nice bytecode set, nice distribution mechanism in class files and jar files. So it made sense that you might want other languages on there. But other than that, there was not really any explicit support. The JVM was designed for Java originally, and so it's had to evolve a bit over the years to support new languages. Despite this fact, language authors over the years have targeted the JVM in various ways, using various tricks to try and make every language on the planet run on top of the JVM. There's even implementations of C. There's implementations of native platforms. If you want a fun project, look at Nested VM. It's an implementation of the MIPS hardware platform on top of the JVM, and it actually works. And there are literally hundreds of JVM languages now. You know many of them. There's all sorts of very obscure ones as well. Well, unfortunately, the JVM was a bit of a mismatch. There's a lot of tricks that were required. Usually these tricks would end up defeating some of the standard optimizations. And so languages weren't able to get the performance they wanted out of the JVM, weren't able to match up to Java as far as raw speed. So if we look at JVM languages through the years, some of the early implementations were Python, JPython originally, which changed its name into Jython later on, and JavaScript in the Rhino implementation, both of those before the year 2000 even, so only a few years after Java even appeared on the scene. But really there was no official backing of any of this by Sun during all of this time. They appreciated the efforts to bring these languages to the JVM, but didn't do any outward work to really embrace the idea of the JVM as a multi-language platform. That changed in 2006. Myself and Tom Enabo, the two JRuby guys, were hired by Sun primarily to work on JRuby. A secondary job of ours was to work with the JVM team at the time to figure out whether we need Invokedynamic, what it would look like, and how we can make sure it fits the needs of languages like Ruby and JavaScript and others. And after a lot of work on the JVM side, a lot of experimentation on our side, Java 7 did actually ship with Invokedynamic in 2011. So what is this Invokedynamic thing? How many people feel like they have even a little idea what Invokedynamic is? Okay, so most folks, about half the room has a little bit of an idea. I asked this question to a lot of people, or people will come up and ask me, and I'll turn the question around on them, and I get a lot of different answers. So Invokedynamic is just a new bytecode, right? It's just a new bytecode that does something in the JVM, has something to do with doing calls or methods or something. Well, that's true, but what does it really mean to add a new bytecode to the JVM? There's semantics around it. There's some behavior that goes along with it. And is it really just a bytecode? Is it only one new bytecode added into the system? The JVM's got a new trick, and then you're done? Well, obviously that's not quite true. There's a lot more to the story here. Is it a new form of invocation? It says invoke, right? Invokedynamic, some sort of dynamic invocation thing, right? Well, that's one use, but there are many other possibilities, as hopefully you'll see during the rest of the talk. So that's not quite true either. It's only for dynamic languages, obviously. One of the complaints when Java 7 came out by Java developers like yourselves was that they added new features. They didn't add many new features, and one of them was solely for dynamic languages. Well, again, it's not quite true. Invokedynamic is now being used to implement Lambda forms on Java 8, and there's a wide range of potential that the Invokedynamic gives you that's much broader than just dynamic dispatch, dynamic typing. So we get rid of that one too. So really, the way that I've been defining Invokedynamic to people, and it seems to be the clearest definition I've found, is that it's a user-definable bytecode. You've got a list of all these different bytecodes in the JVM, but Invokedynamic was added to allow you to define the behavior, to tell the JVM what your language needs or what your library needs in a very direct way. And then in order to make that bytecode have the right vocabulary for the JVM to optimize it, you get a new API filled with method pointers, field pointers, and various adaptations that can wrap around them. So you get faster than reflection pointers because they're much more direct and the JVM understands them as a direct reference to some method in the system. But you can have user-defined argument processing, argument juggling, flow control wrapping around those method pointers, exception handling, various ways that you can wire up something sort of like a java.lang reflect method, but using your own rules and your own definition. All right. So now we actually are kind of getting to the point where we can start to grasp a little bit of what Invokedynamic is. We've got the invoke side, which is this user-definable bytecode. And we've got this dynamic side, where you can take method pointers and use them to compose basic operations in the language that the VM will understand. You take the bytecode, you take your method handles, you put them together, and the JVM can optimize them together. And if we want to look at this actually in terms of what the specification, what the API is, we've got our bytecode, the Invokedynamic bytecode, plus a bootstrap method that the JVM calls to find out how to implement this bytecode, and the method handles API, which is all of our method pointers, our adaptations, and so on. So let's continue on from here. If anybody has the ability to clone a repository, all the code that you're going to see here is in my GitHub account on an indie deep dive. We'll start off with method handles because I think it's easiest to understand from a Java developer perspective because it is just a regular API at the JVM level. So method handles, as I mentioned, are basically function pointers, method pointers, pointers to field accessors, and also the ability to write into and get data out of arrays. So where you would do, where you'd get a java.lang reflect method object before, with method handles, you'll get a method handle object that behaves in a very similar way. You can add to this sorts of argument manipulation, insert arguments into that process, currying. Curry an argument into that handle so that you'll always have it available and can just call it directly, rather than having to wrap it with a utility class or wrap it with a piece of utility code. You can have flow control, so that you call this method handle, and based on some test, it will branch one way or another, two different targets based on some Boolean result. And probably the most important part of method handles is that this is kind of a raw intermediate form, a raw language that the JVM understands and can optimize. Whereas little utility classes and one-off anonymous classes that you might pass around look like Java code but may not be optimized as well as a direct call, as a direct invocation. The intent and hopefully the guarantee as optimizations continue is that method handles will be as fast as making a direct call without any intermediate library, any intermediate adapter, or without using java.lang reflect, which is much, much slower. Okay, so the package we're looking at is java.lang.invoke. The java.lang.invoke package contains lots of different classes, utility classes for Invokedynamic, but primarily the ones that we're looking at are method handle, which I said is an invocable target, an invocable function or field pointer, plus adapters that wrap around it. Method type, which is basically just a structure that represents the type of all the arguments and the return value for a method handle, for a call, and so on. And the method handles class, which contains utilities for acquiring handles, adapting handles, and doing other things with them. So we're going to look first at MethodHandles.Lookup, capital L. An inner class in method handles. And this is the first place you're going to go to start playing around with method handles. This is how you get access to method pointers via find static, find virtual, find special, find constructor. Essentially, this is how you pull those pointers out of a given class, or field pointers, getters and setters and so on. Once you have that in hand, you can invoke it and call those methods. Let's take a look at what that actually is in code here. So up at the top, we've got MethodHandles.Lookup. We're grabbing lookup objects to use for doing some of our method pointers here. And the two basic methods on method handles that gets you access to them is lookup and public lookup. Public lookup, as you might guess, gives you a lookup object that can only see public fields and methods. It's the simplest one. So if all you're doing is something similar to what java.lang.reflect does, all you're accessing is public fields or methods, this is a quick way to get a lookup object and know that you're always going to see just the public elements. The lookup method, however, is special. The visibility that it has into classes all over the system is based on the point where you call it. So, for example, I have private data, private fields or methods within the basic handles class. The lookup method here will allow me to see them and get pointers to them and invoke them from anywhere. Even give those pointers out to other people so they can invoke them. It's an acquire, a lookup time check to make sure I have access to them. Whereas the public lookup version will not let me see the private elements. Fairly simple for those two items. All right, so let's continue on here. Now, hopefully you can see the example Java code okay. Trying to show a little bit of here's the standard Java code you'd have for getting a property or printing out hello world, right? Everyone's seen this code 1,000 times. Let's implement this or build this into a method handle. So here we have two different signatures that we're using. The getProperty method returns a string and takes a string argument, where the println method returns void and takes any object. We're using that overload of println here. So we have our two method types. We go to our lookup object, and we ask for, on the system class, the getProperty method with this method type. So far, looking pretty much like java.lang.reflect APIs. Get a class object, you've got a name, you've got some types, and then you get a handle back. Similarly, on printStream, we're going to get the println method using the type that we defined above, returning void and receiving object. Now we have two essentially like java.lang.reflect methods that we can invoke. Let's give that a shot here. Okay. So, not much to this example. You'll see the print line for the hello world if we run this. Run file. Okay, so there's the hello world. The property looks up Java home. We're not printing that out. But you can see that we've basically got a little handle, just like a Java.lang.reflect. Let's go back into the slides here. Oh, actually, I still have the getter example, too, that I can show. So down below here, we have an example of using the getters. So when we do println, we access system.out, a static field. In order to get the static field accessor out of a class, this is something that you can do with the java.lang.reflect field, for example. System.class, the out field, which the type of it is printStream, and of course we want the static getter so that we can access that. And then we have our system.out method handle that lets us access it every time we call invoke. Okay. Down below, we'll do an instance setter. So we've got a name field on our little myStruct class. myStruct, name, and the string type. All right. Now, what can we do with these? Can we add a little bit of magic to them? Well, first of all, let's take a look at this actual invocation up here for the system out and the system out print line and the get property. One thing you might notice here is we're doing this get property, and casting this to string is not particularly unusual. This particular method returns object just like it would in a standard java.lang.reflect method. So that makes some sense. But why are we casting this to object here? We all know that if we're passing a string into a method that takes object, it doesn't care. And even when we're calling in reflection, we can pass a string, and it will handle converting it into the right type, casting into the right type. Well, the reason for this is a little bit obscure, but it's something that'll bite you if you don't know about it. So I want to make sure you know. Where is it here? So there's several methods on method handles that are what's called signature polymorphic. Normally, when you compile a piece of Java code, the signature that it puts into the bytecode is based on the method it finds on a target class. It always uses the actual signature of the definition of the method. For signature polymorphic calls, it uses the signature, it builds the signature based on what types it sees on the caller side. So if we're going to call a method handle that expects an object, we need to make sure we've cast that to object. Otherwise, it's going to try and pass it as a string. It's using the call side types rather than the receive side types. Something to keep in mind as you're playing with some of these methods. The easiest way to get around this is to use invoke with arguments, which will do a lot of the casting, boxing, unboxing, and so on that you would expect out of something like java.lang reflect method. It's probably worth mentioning why this is. The reason for having signature polymorphism, when you do a call, even though this signature in invoke shows itself as being a var_args call, because it knows the actual signature at the point of call, there will be no boxing. It will pass all types directly through, and it will not have to do any conversions along the way, because it already knows you've passed in the correct types. This is one of the key reasons why invoking method handles can potentially be so much faster than calling java.lang reflect method, which has to box everything into an array, box integers, and box primitives into boxed values. All right, now back to the fun. So, lots of different adapters that we have access to. Argument manipulation and modification I've mentioned, flow control and exception handling. This is sort of like taking a java.lang reflect method or writing your own little utility class that juggles arguments around, does some conversions on them, perhaps upcases strings or encodes some password, but basically doing this as part of the method handle chain. So all you have still in hand is an optimizable chain of handles that the JVM will be able to inline and optimize like a regular call. So there's several different versions of these. You can insert arguments so that every time you invoke, it already has the argument present. Basically a currying operation for anybody familiar with the term. You can drop arguments. If you know that some of the callers are going to be passing in arguments that aren't needed, you can drop them along the way to the target call. Permute is sort of a super drop. You can drop arguments, you can duplicate arguments, and you can reorder arguments, basically by specifying the indices of all the arguments that you want to carry along through to the target. Now, there's a little bit more complicated modifications you can do. Filtering allows you to say, from this point in the argument list, call a certain function or call a certain method handle of mine to convert these arguments in some way. Like I said, maybe you upcase a string. Maybe you split a string into several elements. The filter runs, turns the arguments into whatever your method returns, and then proceeds to make the final call to whatever target it is. Folding is similar. All arguments get passed into your function. The result of that is reinserted back into the arguments. Casting, not too complicated, just converting the apparent type, the visible type of those objects to whatever you need on the target side. And then splatting and spreading, turning things to and from var_args. Let's take a look at a couple examples of these. Okay. So now remember here, we had our getProperty method handle that was basically bound to system.getProperty. We have our printLine method handle that's bound to system.out.println or printstream.println really. We don't really want, we basically want a handle that does getProperty Java home every single time without having to pass it in. That's what our utility class requires, our utility handle requires. And similarly on the print line, we'd like to have an object in hand that always has system out available. and knows how to just do a print line directly, rather than us having to pass it in every time. So what we're doing here, we do an insert arguments wrapping around the get property call, and the 0 argument should always be java.home. Every invocation from then on will just be a bare invocation because it already has that property name in the method handle. Similarly here, inserting an argument wrapped around our print line method handle to the system out field. And once this is bound, all we have to do is do a call as we have here and here. So invoke with arguments, again, I mentioned we're getting around some of the signature polymorphism stuff. Get Java home now can just be invoked directly because it always has that string available to it. And print line can always just be invoked with whatever it is we want to print out. We've created a little utility class without having a separate inner class or piece of Java code anywhere, without generating any code on the fly. All it is method handles that get composed together. Let's take a look at filter down here. So for filter, we might want to have a little command pattern sort of thing that transforms all of these. Again, like I mentioned, the example of doing 2 uppercase. Now we could have yet another little tiny adapter class, another tiny anonymous class that we pass everything through, but that's not ideal. Certainly not ideal for performance purposes because we're going to be using this in a lot of places. We've got these extra hops. We're adding a little bit more overhead because of that. So let's take a look. We've got 2 uppercase on string. We're now getting a virtual method here. So we've got the string class, 2 uppercase, and the method type is that it just returns string. You call it on a string object, you get a string back. Okay. So now, because we have to have the types match all the way through here, this is doing a casting operation. So we've got our 2 uppercase, which expects that it's going to receive a string and get a string. We want that to take any object and do the casting for us. So we're going to say, let's pretend that this takes objects, do the cast to string as needed. And then we're going to wrap that around print line. So we've got our system out print line, which has system out already bound into it, and we can pass any string into it. We wrap that with this filter, so that the 0 argument, the self object, the this object that's passed in, will always go through this uppercase filter. So now we have a single handle that can uppercase a string, grab system out, and print it, just by calling the one method. And that's what we get here. Let's try running this. Comment some stuff out here. Okay. So we'll run this. We will see that it actually does print out in upcased form. Again, not having to generate any code, not having any little utility classes internally, now we have an optimized pointer that does all of these things as one batch. Okay, there's lots of other these. I'm not going to show drop, and I might show permute a little bit later when we get to the Invokedynamic bytecode part. But you can play around with these and try them out. What I do want to show is flow control. Sometimes you may have 2 different target methods that you want to be called based on some Boolean result. Again, you can build a utility class and stuff both of those methods into it, and then check that Boolean every time and have yet another little class floating around in the system. But with method handles, there's a couple built-in ways to do this. The first is called guardWithTest. This is a method on the method handles class, and it's basically just a Boolean branch. You give it 3 handles. You have a test, or a condition, you have the true path, and you have the false path. And what it'll do every time you invoke it is invoke the test and the condition, test whether the Boolean is true, and then call appropriately based on that. Switch point is similar, but there's no test. The only test it does is whether it has ever been turned off. So it's similar to guardWithTest, but it's true until it's false, and because of that, the JVM can make certain optimizations. It knows it's always going to be on until it's off. Once it's off, optimize that false path straight through all the time. Let's take a look at these in code. All right, so our first example here, I don't think that helps readability much, does it? Try this. our little upper-downer class that will basically, depending on some random Boolean, it will either upcase or downcase the string. Of course, a little bit contrived, but perhaps you're trying to confuse someone in your team as to why it's randomly doing this. So we've got our uppercase method handle already, which we acquired earlier. We'll do the same thing for lowercase. So on the string class, we have two lowercase that just returns a string. Now we want to build our test. So our test for up or down, whether we should do upcasing or downcasing, is in the basic handles class, this class that I'm showing you. And it's a method called random Boolean. I won't show you the implementation, it's just random.nextBoolean, basically. And all it does is return a Boolean value. Now, like I said, the test is going to be passed in all of the arguments. All three handles get all of the arguments that are passed to it, because you might want to use some of those arguments along the way. So we're actually just going, since we don't care about the string that we're actually being called against, we're just going to drop that. So all we're doing is basically just getting that Boolean randomly. We do our guard with test call, and I've statically imported these just to make things a little bit quicker. I think it keeps sanity in code like this. So guard with test, and we have our test handle, we have our true path, and we have our false path. So now we have a little wrapper that will either upcase or downcase, takes any string, returns a string. Let's do our filter again. So we've got our system out print line, and this time we'll filter it with our little randomly up-down case handle that we've got here. Let's uncomment this. Make sure I comment that one out. And we should see, when we run this, that it will randomly upcase and downcase these. And just to show that it's actually random, there, it's different again that time. So now we have a utility class that performs some test, in this case just a random Boolean check, has two different branches that it might follow, passes this string based on uppercase or lowercase to system out, and does the print line for us, all in one handle now. Let's look at the example of a switch point. It's also very similar. This is roughly what the code would look like if you were to implement it by hand. You've got volatile semantics on this switching of this value off, switching of the switch point off. If it's on, we're going to do the uppercase path. And once it's been switched off, we will do the lowercase path forevermore. Like we had above, it's fairly simple. We've got our two uppercase, we've got our two lowercase, and these methods don't actually print out, but you can see the results on the side here. Up until the time when we invalidate this switch point, basically turn it off, it will do the true path, and then it will use the false path from the time that we disable it. And there's random Boolean. Now you can see it. Okay. So I'm not going to show these. You can do exception handling. Basically, you take a method handle that represents the body of code you want to wrap, an exception type that may be thrown from that body of code, and then another handle to the exception handler. You can basically programmatically build up exception handling around a method handle. In order to do that, you also may need to be able to rethrow an exception or throw a new exception. So there is a throw exception method on method handles that essentially just throws the only argument it's passed. All right, so that's method handles. They're really easy to find, really easy to play with. It's just a standard Java API. You can start trying that out today. But the other half of Invokedynamic is very important as well, because it's how we get new languages, new JVM features implemented. So let's look at the actual bytecode now. So what were the goals? Taking a step back for a moment, the goals of JSR 292. Well, we've got a user-definable bytecode that we want people to be able to do whatever they want, whatever they like with. Full freedom to define VM behavior in an optimizable way. Fast method pointers and adapters, so a better than reflection API that the JVM knows how to optimize. And again, all of this trying to be as close to optimizable as regular Java code as possible. But perhaps the most important goal here was to make something that would avoid the need for any future modifications to the JVM bytecode set. We want people to be able to redefine what it means to run on the JVM by using this bytecode plus these different handles. Now, that's a little bit obscure, so let's take another step back about JVM 101 here. There's about 200 opcodes in the JVM. 10 or 16, depending on how you count, are basically endpoints. And what do I mean by endpoints? Those are invocations, virtual, interface, static, and special, field accesses, and array accesses, loads and stores. And this is what I mean by 10 or 16, depending on how you want to count, because there's different types of arrays. So all Java code basically revolves around these endpoints. Everything you do in the system, if you ever want it to have an effect, will have to hit one of these. It'll have to make a call to print something. It'll have to make a database hit. It'll have to update some data in memory somewhere. The remaining nonsense is all just noise for the most part. Stack operations, local variables, branches, flow control, stuff to just get you to these endpoints. Now the problem is that we've got these 200 operations, and all bytecode that loads into a JVM has to fit within these 200 sets of operations. You can't really go outside this. So what if your use case doesn't fit for this? Dynamic languages are an obvious one. We don't have the types necessarily. We have to lazily or have a deferred lookup to find the method to call. Or lazy initialization. Oftentimes we want to be able to initialize something lazily, but still have it optimized well from that point on. And basically a whole bunch of non-Java features, like lambdas, like closures that are being added in Java 8, using Invokedynamic because it makes it easier for them to build a lazily initialized closure object that from then on is optimized and fast. So let's look at what some of the invocations look like. This is a nice subset of bytecode to follow and understand. We've got our 4 different types of invocation here: static, virtual, interface, and special. At the top, static methods are pretty straightforward. Virtual invocations are method invocations against a concrete type, whereas interface invocations are method invocations against an interface type. Again, fairly simple. Most people don't know what special invocations are because you don't normally see them as invocations in the same sense. But this is constructors, this is super calls, this is private method calls, and so on. Now, if we map these into bytecode, it looks something like this. We've got invoke static of system current time millis. With our signature there, the J means that it's returning a long. Similarly, math.log takes a double and returns a double, and on down the page here. All of these just using the same simple bytecode with a target class, a signature for the call, and the name of the call that it's going to make. And this is pretty much it for invocation. Before Java 7, if we wanted to do any other sort of invocation, we're stuck with these operations. So let's kind of break these down and see what they actually do at the JVM level. Invoke virtual, actually all 4 of these have very similar sets of operations. So invoke virtual and invoke interface are probably the 2 that are most similar. They check that the object being called against is of the correct type, so we don't have the wrong object type in hand. We confirm that the arguments are the correct type for the call. We then go and look up that method on whatever the target class is. Probably cache it somewhere so we don't have to keep doing this logic over and over again, and then do the invocation. Invoke static is a little bit simpler. It mostly just has to confirm we got the correct arguments in hand. Go and look up that method on the target Java class, and then cache it and invoke it. There's no receiver. Oftentimes these can optimize much more quickly because there is always one direct target, one known target. Invoke special is a little bit more complicated because we do some additional visibility checks, locality checks. But again, not a whole lot of difference between these. What we get with Invokedynamic is a completely new set of operations that hooks back into what we want to define. So the first thing that happens when the JVM encounters an Invokedynamic is to call our code and ask what to do. Call our bootstrap method. What am I supposed to do at this point? I've got this call and with this name. It takes these arguments. I don't know how to do this. You need to wire it up for me with method handles. So the bootstrap basically prepares a little call side object, which is just a holder, a pointer to a method handle, wires it up to some target method or some target field or whatnot, and then from then on, the call site is used to locate what that target is. You have then defined exactly what happens for this particular Invokedynamic bytecode at this point in the code. A little bit more graphical demonstration of what's happening here. Imagine that this lovely switchboard operator here is our JVM, okay? And we've got our code running in here, and we encounter an Invokedynamic bytecode. Someone makes a call. This comes to the JVM, and the JVM doesn't know what to do with it. The JVM has to ask us, or has to ask our bootstrap method here, what am I supposed to do with this method? So we've got our bootstrap method on the side. The bootstrap method goes and wires up all these handles to say this is exactly what you should do. You should call this method, you should set a field on this class, so on and so forth. Those method handles then will point to some target and go back to the JVM. So the JVM now at this point sees only a direct path from that bytecode to our target method, even though we've done this bootstrapping process. And from then on, this is what happens to all future calls. It just goes straight through to whatever target we've wired up with method handles. And you can start to see the power of this, the ability to have a bytecode that you define in user code exactly what it does. It may not be a static invocation. It may not have typed arguments at all. All right. So now let's put all of this stuff together and actually see the bytecode and method handles working together to do Invokedynamic. So some tools I'll be using here. Most folks should be familiar with ASM, pretty much the de facto standard bytecode library, very likely to be included in at least OpenJDK, very likely for a future version of Java. I'd be surprised if we didn't have a standard API based on ASM as part of JDK. JITescript, which is a nice little DSL or a Fluent wrapper around ASM, lets you build it a little bit more lightweight, not as much boilerplate code. And then a library of mine called Invokebinder, which, rather than doing this wrapping of handles on the way out, using these long names, using some obscure structure, is another little DSL or Fluent API for building up these method handle chains. And you'll see that start to come into play when we look at some of these examples. Okay, so first example I want to show is just a trivial case of binding. We've got an Invokedynamic. We just want to wire it up to the method right away in the bootstrap, and we're done. We don't do any magic with it. We don't change what method it sees later on. It's just a simple method that's going to return string, and we'll print that out. Let's go out. Let's go look at our code. So a simple binding here. Comment that out. Okay. So ASM has its own little handle object to represent, at bytecode generation time, a method handle, because the method handles basically go into the constant pool, like strings and integers and whatnot. So I've created some utility code here. I'm going to create a new runnable that has these 3 bytecodes, roughly 3 bytecodes in here. We're going to do an Invokedynamic. The name of the call is foo. The signature is just going to be returns a string. And you're going to use this simple bootstrap method up here to define what's going to happen. Now let's actually try and run this, and you'll see as we step through it what actually happens in the Invokedynamic binding, which is really cool. Okay, runs and it works. Let's find our simple bootstrap here. Okay. So I'm going to set a breakpoint here. If it'll let me, there we go. And we'll debug this file. Okay, so we're at our first run. We've generated this code that has an Invokedynamic pointing at a particular bootstrap. Set a breakpoint down here and let it continue to run. And what you'll see is, since this is the first time it's encountered it, it will go into our bootstrap. Now, since we don't need to change what method handle it sees after this, we're going to use what's called the constant call site. Constant call site needs a handle when it's first constructed, and it's never going to change after that. So constant call site, that's going to make a static call to whatever method it was. Now remember, from the code, it was just the foo method. Going to call the foo method with whatever the type was. Up here you can see it's just returning string. And here is our foo method that it's actually going to call. Got a little static counter to show you that it's calling it repeatedly. And we'll put a breakpoint in here. So now if we continue to run, we've got our constant call site, we're binding it to this foo method. The next thing we see is that the JVM does do that foo call, actually goes into the method that we've given it. So we do our first printing. Now the interesting thing, if we continue to step through here, I'll set some more breakpoints here. We'll continue to run. Now, okay, we're done with that first call. What's going to happen for the second one? Well, since we've already done the binding, we've already done the bootstrapping, we don't go through the bootstrap anymore. We end up going straight into foo from then on. So every single time this is going to be called, the bootstrapping process is now out of it and we'll go straight to our code. All right. Now, let's look at the second example, because it's a little bit more interesting and starts to get towards our final goal of implementing a little toy language. So we want to actually modify the call site at runtime, change the method that it's calling as we're going. So we're going to basically just toggle between two targets. We're going to call the first method the first time, then the second method, then back to the first. Each time we call, it's going to switch which method we're calling. Similar to, if you had multiple targets for a dynamic language, you'd want to be able to pick the right one at runtime and then call that, rather than always calling the same target. So in order to do this, we're going to take a call site object, a mutable call site object, and pass it along into our first logic and pass it into our second logic, so that after they do it, they can change the target for the next call that comes up. So it's a trivial example of late binding, modifying the call site, and this will be the first time you'll see some invoke binder as well. All right, let me go up and comment this out. We'll switch to the other example. Okay. So here we're doing our mutable call site. Again, similar to the other one, we have our ASM handle to a bootstrap method, in this case, mutable call site bootstrap. We've got our runnable, and this is a little bit simpler. We're going to invoke dynamic. The method we want to call the first time is called first. We're looking for a signature that's just returning a void, no arguments, no return value, with that bootstrap. If we go down and look at the mutable call site bootstrap here, it's a little bit more code. Actually, there's an interesting piece here. Oh yes, okay, the bootstrap. So here we're creating a mutable call site. This is a standard class in java.lang.invoke. We're going to find static the method that we wanted to call first, which is just called the first method, first. But we want it to return void and take this lookup and mutable call site objects as well, so that we can change it on the fly. We can change what method is going to be called after the first invocation. With this handle, we can insert arguments. So at the 0 point, we're going to insert lookup and the mutable call site so that they'll be passed through. Now, you can see how this gets a little bit complicated to do with the standard method handle APIs. Lots of lines, a lot of noise. A little bit more simple is to use invoke binder. Invoke binder says, starting with this signature, a void return value with no arguments, insert 2 arguments into that chain, and then statically invoke whatever that method is. And it already knows what the types are because it carries it along. So a little bit cleaner API for getting that handle out. We're going to set the target for the first call, and then we return this call site to the JVM so that it can stick it in place in the code. The first method, which is going to get called the first time through, it's going to get a binding to the second method, which looks similar to the code we had before, from void, insert the lookup and the mutable call site, do the static invocation. It's going to change the target on the call site, and then it will actually print out that it's in the first method to show you that it's invoked. The second is the same, basically just switches back to the first. So they'll toggle back and forth each time. Let's give this a try. Okay. So we'll debug through this. We're now at the point where we're setting the target. We'll return out of the bootstrap and never come back to it again. Now we're in the first method, and the JVM has called this for us. We've got our invoke static that we're getting. We're getting our reference to the second method. And we print out first there. So we've done the first call. Second time through, it does the second call. And the third time through, it'll be back on the first. And it'll just continue to hop back and forth between these two. Now we've kind of got the basic utilities, the basic tools we need to implement a little language. Okay, so dynamic dispatch. Now the case is we don't know the target method at compile time. We need to dynamically look it up after the bootstrap. Rather than just always going to the second method or the first method, we need to look it up based on arguments that are passed in, and then rebind the call site to the proper method. So we've got a little language here called stupid script. It has only 3 basic operations here. You can push a value onto the stack, which must be a string, always. You can do a call, which basically pops the number of arguments given, the name of the method, and does the invocation. And you can define little functions within the language as well. There is one built-in function called print, so that we can actually see what it's doing. So our implementation is just going to be a simple parser that generates the AST. A compiler will walk that AST. The top-level code goes into the run method, similar to our other runnable examples, and then definitions create additional functions. A little simple hello world in our language, defining a function in our language, and calling the function. All right. So in the last few minutes here, we'll show the very basic parts of stupid script. Okay, we've got our main. It's always just going to read from this file. Like I said, it's pretty stupid. Here is our script, which is basically what you saw in the slides. Define a goodbye method, push goodbye, or push print on there as the method to call, push the value to pass it, and do the call. Down here, we push goodbye onto the stack, and then invoke our goodbye method. So that'll be parsed and compiled. We're going to gloss over some of the details of parsing it here. Here's our print. We're actually going to end up calling the one that takes an argument. Here is our bootstrap. We're going to basically just wire things up to our send implementation. And now send is just going to look at the method name that's passed in, find that method either in the utilities, the built-ins, or in the user's class, the class we've actually just defined, bind it into the mutable call site here, and then do the first invocation. So there, we've actually implemented a very simple language. If we want to look at what the compilation of that language actually looks like, here is the entire body of the main part of the compiler. If it's push, we're going to do a load constant at the JVM level, load that string onto the stack. If it's a send, we know we've already got the method name and the arguments on the stack, so we're going to load our self, since we may be calling a self method, a method that the user's defined. Depending on how many arguments, and stupid script only supports 0 or 1 arguments, so hopefully that's enough for you. We're going to call with the name here, the self object, and then potentially in the one arity version, we've got string.class. The string is actually being passed in. And then def and def1 are our primitive ways of defining a method that takes no arguments or a method that takes 1 argument. And now when we run this, we'll actually see the output of our stupid script. Go here and run file. And there we go. Goodbye world. Hopefully you've got a little idea of how quickly and easily you can build some cool things with Invokedynamic, how powerful it is today, and how powerful it's going to be in the future. And you'll be able to go out and do some amazing things with it. So if you want more information, I blog about this stuff reasonably often. You can follow me at Hedius and hear all about Invokedynamic and JRuby. Like I said, the code is on GitHub if you want to check it out and try playing around with it yourself. And these slides are actually already up on SlideShare. So if you check my Twitter stream, you should be able to find them. Thanks very much. And I know we're right at time. Are we allowed to take any questions, or you can come and catch me afterwards. I think we have lunch after this, right? So, thanks a lot.